Now let's try out number 3. We have a table we're given off to the right hand side, and we're asking which domain must be changed in order for this to be a function. Well, we know that anytime we want a function, each of our values in our domain must be going to exactly one output value. So we have this discrepancy here where we have 2 values in our input that are going to 2 separate values of our output. So we want to do something to address this here. So let's see. Letter B says the ordered pair of 3, 4. So if we change this domain value for our ordered pair 3, 4, we'll have a different value instead of 3 there, which could give us a unique input for that output, which is exactly what we want to do in order to make this a function here. So I think letter B is our best choice for number 3. Okay, why don't you try out 4 and 5 on your own? Pause the video and see if you can work through them, and then once you're feeling confident, you can unpause and we can go through those 2 together. Okay, let's start off with number 4. So we have our domain, our given set of input values, and our relation y is equal to 2x plus y. So if we want to find our range, all we need to do is plug in each of these points for x. So y is equal to 2 times 3 plus 7 gives us y is equal to 13. Then we have y is equal to 2 times 4 plus 7, which gives us y is equal to 15. Y is equal to 2 times 5 plus 7 gives us y is equal to 17. Then we have y is equal to 2 times 7 plus 7 gives us y is equal to 21. And we'll do one more. Y is equal to 2 times 10 plus 7 gives us y is equal to 27. So now going through our list of all of our answers here, we can see that letter D gives us all of our proper 5 choices: 13, 15, 17, 21, and 27. Now for number 5, we have our 4 points listed, and we just want to pick out our domain and range here. So our domain is going to be all of our x values here are -6, 1, 4, and 9. So it looks like either one of these 2 give us that right domain. And for our range, we're looking for the outputs of 8, 1, -7, -22, which looks like this one was close, but they've left out our -7. So letter C is going to be our proper choice here, where we have all of our x and y values properly organized into our domain and range. We've got a few more terms to go over in order to finish up with today's lesson. So next we've got a relation, which is a set of ordered pairs, a mapping of an input value to an output value. Then we have a function, a relation in which the x values do not repeat, and our vertical line test, which is used to determine if the graph of a relation is a function, and we already saw a couple examples of that already. So now we have, in the table below, the numbers in the rows represent ordered pairs. The relationships between the numbers is represented by the equation y is equal to 2x. When you double the first number in the ordered pair, the result is the second number of the ordered pair. And the graph shows the coordinates in the table plotted on the coordinate plane and connected with a straight line. So we have our table here and its corresponding graph. Continuing on, let's read a little more about it. We have a relation is a set of ordered pairs that connects a set of output numbers or y values to a set of input values or x values. In the input variable, x is also called the independent variable, and the output variable, y, is called the dependent variable. A function is a relation in which each input number or x value has one and only one output number or y value. The table and graph above represent a function. For each x value, there's one and only one y value. So let's take a look at what we just read. We can see for any given x that we have in our table, we have only one y value that corresponds to it. So each of these is only mapped to one output value. Likewise, within our graph, everything here, no matter where we go in the x direction, left or right, every term or every x value is only given one corresponding output for its y value. So that's what gives us our function here. then we have two more little graphs to consider that we can quickly determine whether or not these are functions just by using our vertical line test. So in this first one, trying to decide if there's anywhere we can draw a vertical line that we can cross 2 points of our graph. At first, maybe it looks like it, but there's actually no place we can do so. So this one results in a function here. For our second one, we can see that it's pretty easy to make up some sort of line which crosses 2 points. So this one we could say is not a function. So it's just a really quick way to be able to look at a graph and determine whether or not we have a function that we're looking at. So let's take some look at examples of those where we have classify each relationship as a function or not a function. So now that you saw a couple already, why don't you go ahead through these three and see if you can determine whether or not we have functions here for each of them. So go ahead and work on those now, and then once you're ready, we can go through them together. Alright, so this first one, there's no place we can draw our vertical line. We've got a nice simple function here for this one. So it passes our vertical line test. The second one, we've got a perfectly horizontal line. Well, that's really easy to see. Anywhere we draw a vertical line, we can only have one intersection here. So this one is again a function. Here our line is actually a little harder to see. It's this x is equal to, looks like 1.5, or x is equal to, yeah, 1.5, 2-ish. We've got, so this is a perfectly straight up and down vertical line, which means we can only draw one line to test our vertical line test right here, which is going to correspond with an infinite number of points that it is interacting with here. So this one fails our vertical line test. We could say not a function, because we have one value for x, and that's being mapped to an infinite number of values for y. So we can say this one is not a function here. Continuing on, we want to determine whether or not we have some functions with some tables. So I'll try out this first one here. We want to look at all of our x terms. We can see that we have all unique x terms here, which is a good thing, and those are all mapped to individual components of our outputs here. So this first one we can say is indeed a function. Then for our second table here, right off the bat, I'm noticing that we have two pairs of -3 and -2, and in each of those they're going to different outputs here. So we have the same input going to different outputs. It happens twice, so we know this one is not a function. Okay, number 3, we're still determining whether or not we have functions here. So in letter A, I can see if I draw this vertical line, I'm intersecting these 2 points, which have closed dots, which means they are a part of our graph. So that vertical line right there shows me we are failing our vertical line test, and we can conclude this one is not a function. Next, this one was similar to an example we saw earlier, where we can draw these lines which at first look like they're failing our vertical line test, but we can see in either case one of these dots is closed, which means we're actually only including one of these points from our graph. So this one does indeed actually pass our test, and we can say this one is a function. Okay, 2 more examples here. Let's go through in number 1, try to determine whether each relation is a function. So I'll do letters A and C, then I'll let you do B and D on your own. So if we've got letter A, we have a repeat of -2 for our inputs for x, and each of these -2 terms corresponds to a different output there. So we have that single input going to 2 outputs, meaning this one is not a function. Then for C, we saw an example similar to this. One vertical line was able to cross 2 points of our graph, so again, not a function. Okay, why don't you pause and work on letters B and D for a moment, and then once you're ready, you can unpause and we'll go over them together. Alright, looking at letter B, I can see that I have this 7/15 here that goes to two separate values of our range. So it's that one input going to two output values, which means letter B is not a function. And letter D, well, this one looks pretty good. No matter where we draw a line, we're not going to get more than 1 point that we're going to cross here. So letter D is actually our only function of the three. Then number 2, Donna claims that y is equal to 2x minus 5 is a function. Which statement best explains the accuracy of Donna's claim? So we have A, it is incorrect because some values in the range are negative. Well, that doesn't matter. We can have negative values in a function for the range, and we should be good to go. Letter B says it is correct because each value in the domain maps to exactly one value in the range. I think that one sounds pretty good, but let's just go through and check C and D and just to make sure. Letter C says it is incorrect because the values of the domain are not the same values in the range. Well, the domain and range don't have to be the same, so that's not something we ever need to consider there. D says it is correct because each value in the domain is the opposite of each number in the range. That's also something that we don't need to have be true for our function. Letter B is the best choice here. It is indeed a function, and that's because each value maps to only one value in our range here. So B is the best choice for Donna's claim. Okay, that wraps it up for all of our examples for today's lesson. I'll see you all in our next lesson. Until then, take care, everyone.